Name is Saeed Al Bakri, and this is my recording for my part two submission for the final project for CSE 546. In this, I'm going to briefly demonstrate the code that I used for this flower classification project and then walk through my experiments, results, and analysis. I'm going to start with a short code demo to show that everything runs and generates the required output, and then I'll spend the rest of the time explaining the figures in the reports. So here's my main .py file. So this thing is 600 lines of code, so I'm not going to show everything, but it loads the training features and labels, explores the pre-processing options with logistic regression, tunes 4 different classifiers using fourfold stratified clause validation, builds 2 ensembles, stacking, and add a boost, and then finally chooses a chosen model on all the training data and produces predictions. I'm going to go ahead and run it now. It's going to take a minute to load in its entirety, but first it'll load the flower trains features and then labels, puts the class counts for that, for the 5 classes. It's going to continue running. Again, it's not the fastest running code in the world. Next, the script runs grid search for pre-processing with logistic regression, then tunes each classifier, and it'll continue to run. You can see here it runs to that. It saves the CV results to these JSONs here, which has already been generated. Then it'll continue to run with the stacking ensemble and add a boost. It'll show the best ones. Now it's on support vector machine, running the grid search for support vector machine. Now it's chosen its best modifier, so it's going to run with that. It's going to do the same with the random forest. And this will also take a minute to run. So random forest is probably the model that takes the longest to run. Funnily enough, I also used random forest for my capstone class, and that code takes multiple hours to run. So random forest is a notoriously slow to run machine learning model. Yeah, but it also doesn't admittedly have the best performance of a model anyway, so I can't even say that the runtime is worth it, but it does run. Next would be k nearest neighbors. Again, this one runs much quicker. It'll get all of these outputs. It'll save them to a CV. You can see the outer fourfold CV results printed in these. It evaluates the stacking ensemble and the ADA boost right here. You can see some of the results here. For the sake of time, I'm just going to go through and show the outputs while the code is still running, since these have already been generated prior. So it returns the results in these JSONs, shows the misclassified samples here, shows the correctly classified samples here, shows the outputs here, and then of course these are the original ones. Again, this does take a minute to run. Yeah, I have the JSON CV results for each cred search, the classifier output correlations, matrix, and the CSVs listing correct in the results. And then in the plots, I have the confusion matrix. So the training versus validation plots for the key hyperparameters here for each of the classifiers. We see here the confusion matrix, which correlates to the misclassified versus correctly classified samples. And here we see that it's chosen its best model, and it's going to run that, it's going to run that, and it's going to generate to here. So again, we don't need to go into the detail on the results since the report does that. So moving on to the report, we see, I'm just going to walk through the experiments, the main results. So this assignment required 2 normalization options, PCA with 2 choices of dimensionality, feature selection with at least 2 options, 4 classifiers plus 2 ensembles, and evaluation using fourfold cross-validation. So with normalization, I use standard scalar, min-mix scalar. With PCA, I use 32 or 50 components. For the feature selection, I used either k equals 16 or 32, And then for classifier hyperparameter, I use 0.1, 1.0, and 10. So that's a total of 24 configurations. And moving on, just to show here more details on each of these configurations, and also my justification. So 50 produced consistently higher validation performance. K equals 32 yielded higher and more stable F1 scores. And then standard scalar produced slightly better mean validation. So moving on, firstly, I used logistic regression, support vector machine, random forest, and KNN, as I explained earlier, as my choice of classifiers. I used logistic regression as a relatively fast baseline to explore pre-processing options. Moving on here, the plots here show macro F1 for different PCA and K choices, including both mean train and mean validation scores across folds. From these figures, and moving on, just generally we can see that these gave a good balance of performance and stability across folds and low overfitting with these hyper configurations for the hyperparameters. But then actually moving on to the actual classifiers themselves. So with the pre-processing fixed, I tuned each classifier separately. So for logistic regression, I varied C over 0.1, 1, and 10 with L2 penalty. The outer cross-validation results with the accuracy are 0.875, 0.8760, 0.87, and then 0.8748. So train metrics are only slightly higher, so logistic regression is fairly well regularized. In the grid search, larger C values like 10.0 gave slightly higher train scores, but not much improvement in the validation. So C around 1.0 is a reasonable compromise. Then we see here with that, with the PCA components and the select K best. And then moving on to SVM. So this is just showing for SVM I tuned C equals 0.1, 1, and then 1.0 gamma scale, 0.001 and 0.001. The C versus F1 plot shows that for very small C, the model is underfitting with a low train and validation F1. As C increases to 1, both train and validation improve, and then at C equals 10, train scores are extremely high, but validation F1 doesn't improve much, so the train test gap widens, which shows a sign of overfitting. So I selected a configuration around C equals 1, gamma equals 0.001, where test accuracy is a little bit better. Moving on to, and then we can see here just some visualization of SVMC versus F1 scores. Moving on to random forest, I tuned with the N estimators around 100 to 200, the max depth either none, 10 or 20. With the min sample splits, it was either 2 or 5. So it shows that going from 100 to 200 helps a bit, but the biggest effect is from depth. With unrestricted depth, giving nearly perfect train performance, but only about not the best test accuracy. So this is, of course, classic overfitting, extremely high train scores, and a noticeable gap with the test scores. And then again, some visualization, the N estimators versus the F1 macro. Moving on to K nearest neighbors, I varied K with 357. The weights are either uniform or distance. So small K like 3 has a very high train accuracy, but more variance and slightly worse validation F1. So overall, again, same here. So overall, SVM is the best single model in terms of accuracy. Logistic regression is simpler and fairly strong, and random forest and KNN are competitive but show more overfitting. Onto the ensembles. Before building the stacking ensemble, I looked at how correlated the classifier's outputs are. I used cross-validated predicted probabilities from each tuned classifier. There were very high correlations. All the models largely agreed, but there's still some complementary differences, especially between linear regression, SVM, and random forest. Based on performance and correlation, I chose logistic regression, SVM, and random forest. And then going on, talking about stacking versus AutoBoost. So stacking slightly improves F1 ROC. AutoBoost is notably worse. So AdaBoost underperforms both the single SVM and the stacking ensemble in this data set. And then moving on to the misclassified samples. To satisfy the requirements, I analyzed the error patterns. This is the confusion matrix. Most masses on the diagonal, which is showing pretty high overall accuracy, but some confusions appear between visually similar flowers. Of course, moving on, we can see here that most of the correctly identified samples are flowers with, stronger red or pink petals, ones that have higher contrast, whereas ones that are misclassified are the ones that kind of look similar, are in similar backgrounds, or they're so small that they're barely legible, and also generally low contrast in the color. Most of the time, the misclassified samples default to sunflower. Of course, this is because sunflower, when you think of a flower, you think of sunflower. And yeah, so a daisy image with a clear white flower on a simple background is correctly classified, whereas another daisy image could be misclassified as a dandelion, where the flower is small, slightly blurred, and the background is cluttered with grass. So these examples justify the misclassifications. They aren't random errors, but they arise from visual similarity, cluttered backgrounds, and feature ambiguities. So to summarize, I implemented a pipeline with 2 normalization options, PCA feature selection, 4 voice classifiers, and 2 ensembles. I used a 4-fold stratified cross-validation with accuracy, macro F1, and ROC AUC, analyzed train versus validation behavior to choose parameters, and finally selected stacking as the best model. I also examined the confusion patterns and individual images to justify misclassified samples. So that concludes my presentation. Thank you for watching, and thank you for this class.